What is up, everybody? Let's talk about concurrency in Go. Now, generally speaking, when you talk about concurrency, two terms often come up. One is concurrency, and the other is parallelism. Now, many people struggle to define what these even are and the differences, so let's talk about that first. So, concurrency and parallelism are often defined as you see here on the screen. Concurrency is out of order execution of multiple processes. So it allows you to run multiple processes kind of out of order or like interleaved if you think about it. And the way that it works is you have your CPU in your computer, it's going to context switch between different processes to kind of give you that illusion that all of these processes are running in parallel at the same time. Think of your operating system, right? There are many processes on the operating system that are running. They're not all necessarily running at the same exact time, but your operating system, the kernel, is switching between these processes very, very quickly to kind of give you that illusion that things are happening at the same time. Whereas if you look at parallelism, once you start executing multiple processes simultaneously, that is at the exact same time as one another, now you're moving into parallelism. And the way parallelism works is it uses multiple CPUs or CPU cores and threads to execute multiple processes at the exact same time. Now, you've probably seen languages that have like concurrent features or what may it, but I like to give an example to like kind of show this and how concurrency and parallelism works for like, the average person out there. Think of yourself like cooking a meal, right? You're chopping up vegetables and then you get a phone call. Well, you're going to stop chopping vegetables and you're going to pick up the phone call, right? That's a context switch. So you're doing these two things concurrently. You were chopping vegetables, but now you're answering a phone call. Now you're on the phone call, you're talking to someone, whatever. The work to chop vegetables is not getting done anymore, right? You're still kind of juggling the task, but you're not actively working on it. But then maybe you want to put that person on hold. So you put the phone down and you go back to chopping your vegetables. This is like a practical example of concurrency, right? You are running multiple processes, you're doing multiple things, you're just doing them out of order. So like the tasks are moving forward, but they're not necessarily moving forward at the exact same time. If you wanted to do that same process in parallel, well, you'd probably put your phone on your head or get like a headset and chop vegetables at the exact same time that you're on the phone with your friend or whoever it is calling. That's my example that I like to use. Either way, I have some code here that I want to talk to you about. So I want to teach you concurrency in Go, but I want to do it in a way that's like kind of easy to understand from any level, right? Like doesn't really matter that we're using Go here. The concepts are Go specific, but like they can transcend different languages that you're using. But before I kind of get into what we're doing here, I like to explain the code that's in front of you so you understand kind of like the setup that we have. So let's talk about it. So I have this main function here, and you can see that I have these variables up top that say the number of files and the read delay. The summary of what's going to happen here is I'm going to create 20 files, right? And I'm going to then read those 20 files with a 5 millisecond delay in between reading each one. And I'm going to do that serially, right? So one at a time. And I'm going to do that concurrently. And I'm going to show you different ways of doing it concurrently and what the performance benefits are of that. But to give you a brief overview of the code here, all I'm doing is I'm setting up 20 files. So we'll look at that function real quick. So this setup function just creates a temporary directory and writes 20 files into it. That's all it's doing. Then I have like these other util functions that we'll come back to, but I just wanted to show you that setup function. Now, after I created the 20 files, every time I run this, I want to like clean them up, right? So I'm creating a temporary directory, dumping 20 files into it because we're going to read them as part of this video. And I want to defer the cleanup of it just so that we don't leave things messing around. Then I'm going to run a function that measures the time it takes to read all 20 of these files, right? So the function is measure time. Measure time just prints the fact that it's reading files. It marks the start time. It actually invokes the function to read all 20 of those files. And then it tells us that it's done and how long that took. And you'll see here, measure time takes a name that we're just using to like, segregate the different like functions that we're calling, right? A serial one, a concurrent one, a blah, blah, blah. It takes the directory of where all the files are located so it can go through them. It takes the amount of time it should delay between reading each file, and it takes a special read function, and that read function is going to be the function it calls to actually perform the serial or concurrent read of all of these files. So that's kind of the TLDR here. And you'll notice that we're going to pass a read serial function here to this measure time, right? This read serial function is exactly probably what you think it is. We're going to get all the files in that temporary directory, right? All 20 of them. And we're going to iterate them one at a time. And we're going to read them all and print out their content to standard out. So let's see what this looks like in practice. So if I run this, you'll see that my function is printed it. It said, hey, we're doing serial work. We're reading the files. Here's file 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way down to file 19. So all 20 files have been read. And that took about 118 milliseconds, right? If I ran this again and again, you'll see that it takes anywhere from 120 milliseconds, more or less, right? Somewhere in that range. So this is reading one file at a time. What's kind of happening here, right? I can't read file 1 until I've read file 0. I can't read file 2 until I've read file 1. So I'm forced to read the files in order one at a time. I can't read more than one of them at a given time. This is not concurrent code. This is serial code, right? It's executing in order serially, one file at a time. Well, we can do better than that, right? So Go has this concept of Goroutines. And Goroutines are a way to spawn another thread almost. I'm going to use the word thread, but it's not really a thread under the hood. It's a Goroutine. But it has a way of spawning like another thread where you can do work asynchronously, right? You probably heard the word async before if you're coming from like a JavaScript or a Rust or something else. But you can execute work asynchronously using the Go keyword. And I'm going to show you what that is. So I'm going to go to my concurrent function here, which is called read wait group. And now this is almost the exact same as the read serial, but we've added some concurrency primitives in here to now read these files concurrently. I'm going to talk about the code first, and then I'm going to run it. So generally speaking, when you're talking about concurrency in Go, there's two main primitives that you're going to be aware of. One of that is going to be the Goroutine itself, right? So the actual Go keyword here that I have highlighted that spawns a Goroutine. And the other one is usually channels or a wait group, but wait groups are kind of channels under the hood, whatever, doesn't matter. But the idea is that there's these primitives that you can use to make your code concurrent. So you see here that up here on line 22, I'm creating a new instance of a wait group, right? Because I want to use this wait group. You might be asking yourself, Matt, what is a wait group? It's kind of in the name. It's a way to wait for a group of work to finish, right? So that's kind of all the wait group does, is it keep tracks of what work is being run and whether or not it's done. And the way the wait group works under the hood is every time you want to do a unit of work, you use wait group add and you say, hey, I want to do one or more units of work. And every time you're done with that unit of work, you call wait group done and you kind of release that work back. And then if you want to wait for all of the work to be done, you call wait group wait. How does this kind of work? Well, wait group starts at 0, right? Every time you add work to it, you add 1. So you add 1, 2, 3, 4, 5, 6, 7. As work is done, you call wait group.done, and that decrements the counter back. So now you're at 8, 7, 6, 5, 4, 3, 2, 1, 0. Once it gets back to 0, the wait call at the bottom will finish. It'll unblock, and it'll move forward. So reading this code, we have the wait group. We're going to iterate over all of the files in our temporary directory. We're going to mark them as being starting one unit of work, right? One unit of work per each file. Then we're going to call the Go keyword, and we're going to say, hey, Go, please spawn a Goroutine to execute this block of code here, right? Whatever is in this block of code, execute this whole block of code asynchronously. So what's going to happen? Go is going to go ahead and spawn a Goroutine, and it's going to continue the for loop and go to the next for loop. So this for loop is going to execute very, very quickly. And what's going to happen is 20 Goroutines are going to spawn, and they're going to start immediately executing depending on how the kernel schedules them. What's going to happen here is we're going to sleep for our delay, read the file, print it out to standard out, and keep going. Now, when this function runs and the for loop executes very quickly, we're going to land on this WG wait at the very bottom here. The program is going to sit here until all 20 of those Goroutines have exited and called WG done. Once that happens, we fall through and we're done running this concurrently. Couple of things that I want to note here that are little gotchas. You got to remember to call WG done, right? Wait group done. If you don't, you're going to have a lingering Goroutine out there, or you're just going to block forever and kind of deadlock the program because the wait will never actually proceed. So make sure that for every time you call add, you call the equivalent dones in order to not keep yourself from deadlocking. And another thing I want to show you is, notice how my go function here is using a function literal. So this is literally just a function literal that says, hey, run a function that takes a fs_dir entry and pass it down here. If I didn't do this pass this entry this way, and I did this instead, and I didn't even pass it like this, I would actually run into a concurrency issue because this entry variable would be captured, right? It would be captured by the for statement. This is a common problem in Go. And I'd get actually the last entry. So common little gotcha here is make sure you're either doing what I'm doing here, which is I'm passing the entry specifically to my Goroutine, or you do the common entry equals entry. So if you look this up, it's called the for loop concurrency thing in Go. It's kind of a known thing that they fixed in, I think, Go 122 or 123. Either way, just keep that in mind. Anyway, back to this. This is the entire concurrent program here. I'm going to spawn 20 Goroutines, try to read all 20 of those files as quickly as possible, wait for all those 20 Goroutines to exit, and be done. Let's run it. So here we go. I forgot to save this. We'll run this right now. And this time I read all 20 of these files concurrently. And what do you notice? So you notice two things. One, it's significantly faster, right? You'll probably ask yourself, wait, Matt, you're sleeping 5 milliseconds every time you read a file. You're reading 20 files. How the heck did you read all 20 files in 20 milliseconds, in 5 milliseconds? Well, I read them all concurrently, right? At around the same time. So I didn't have to wait 5 milliseconds per each file. I just had to wait 5 milliseconds in total because they are all running, concurrently at the same time. And the second thing you'll notice here is that the files are no longer printed, the contents are no longer printed in any sort of order, right? This is all out of order execution, right? This is not 0 to 19 anymore. This is 08, 00, 18, blah, blah, blah. If I were to run this again and again, you'll notice that they print out in different orders each time. This is what we call non-deterministic. Now, when you're doing concurrent programming, you got to think about this, right? Because if your program depends on the ordering of the files or some way, and you're using concurrency, you're going to have to now capture these results and sort them or do something else because they're going to be coming in out of order. Cool. So that's using the wait group. Let's move on to the next one. So instead of using a wait group, you can also use a channel. Now, I'm only showing this example because you're going to see channels in your average Go program. Generally speaking, wait groups are perfectly fine to use, but you'll probably see channels here and there. So I just kind of wanted to show you both parts. Kind of the same code if you think about it. The only difference here is we have this done channel and we defer pushing a value to the done channel and retrieving it on the other side. So what's happening here is we make a done channel. This done channel is used for synchronization. So in Go, the way unbuffered channels work, this is an unbuffered channel. The way they work is in order to send a value to the channel, which is here on this defer line down here, something has to be waiting on the other side to receive it. It's kind of like a handshake, right? If you put your hand out, you can't actually complete a handshake until someone's on the other side to grab your hand. That's kind of how unbuffered channels work in Go. somebody has to be waiting there on the other side. So in this code, we iterate through all the files again, right? All 20 of them. We spawn a go routine for each file. So we have 20 go routines. And we're going to defer this sending of the done channel, right? The handshake that we're doing. And we're going to read our file. So we go through, 20 go routines spawned. And then at the end, we sit here in this for loop and we iterate over all 20 files again. And we say, hey, handshake, 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 handshake. We wait for all 20 of those go routines to signal to us that they're complete, right? To give us our handshake. Once that happens, we're done with this for loop because we've ranged over it and we can exit this function. Now you might be, the keen listener or reader here might be like, wait a minute, Matt, what happens if one of these go routines like never completes the handshake, right? It never signals that it's done. That is a super valid question, because if it never did, you would deadlock here, right? Let's say like 19 of these go routines completed successfully and gave me my handshake, and that last go routine just died somewhere, right? It's gone. What's going to happen? Well, I'm going to deadlock right here in this for loop because I'll never be able to complete the range because I'm going to be stuck waiting. I'm going to have my hand out waiting for a handshake and nobody's ever going to come give me that handshake. So these are the things you have to think about when you're writing concurrent programs. Either way, this is very similar to the wait group function in that it's going to spawn 20 go routines, wait for all of them to complete. Let's see what it does. So let's run this, and you'll see that now we're doing the channel way. We're reading all of these 20 files, and again, we get them out of order, and we take about 5 to 6 milliseconds. If I ran this again, different ordering of files, about 5 to 6 milliseconds. Both the wait group approach and this channel-based approach are pretty much very similar, and they have similar runtime and similar non-determinism. I just wanted to show you kind of two sides of the same coin. What's the problem with both of these? So you can't just use a wait group like this or a channel and spawn hundreds of go routines, right? What if my number of files was 20,000, right? If I had 20,000 files here. Well, both of these wait group and channel methods, they're going to spawn 20,000 go routines. That's a pretty easy way to DDoS your own program, right? So we call this in Go, or just in general, we call this unbounded concurrency, right? There's no bounds limiting the amount of concurrency my program's trying to do. So if I had 20,000 files to read, I'm going to get 20,000 go routines. If I had 2 files to read, I'll get 2 go routines. There's no bounds to this concurrency. That's a problem, right? That's not good defensive programming. That's just asking to get woken up at 3 o'clock in the morning for a page that you're not going to want to deal with. How can we fix this? Well, we can kind of combine the concept of the wait group and the channel into a concurrency pattern known as the semaphore. Now, the semaphore pattern it kind of sounds scary at first, and there's also a package in, I believe, the Go standard library or the extended library that has semaphores in it. But semaphores sound scary, but they're really not. What happens here is we're going to use the wait group like we did before. But in this case, we're also going to use channels, but we're going to have a buffer channel here of size 5. And we're going to say, hey, don't spawn 20 go routines and go crazy. Spawn only 5 go routines at a time. So this for loop's going to iterate. It's going to put something in the concurrency slot. It's going to say, hey, you have 5 concurrency slots to fill, right? You have 5 spaces in this channel. I'm going to put something in that space and I'm going to execute asynchronously. So we mark one of the concurrency slots as filled. We tell our wait group, hey, we're about to do a unit of work. And then we go off and execute that work asynchronously, right? And we do that again and again and again and again. What's going to happen is eventually I'm not going to be able to, all my concurrency slots in my semaphore channel are going to be filled, right? 5 go routines are going to be spawned. They're all going to tell the semaphore channel hey, I'm here, I'm using you. And the next go routine, the 6th one, will be wait a minute, I can't actually give anything to my semaphore channel because it's full. And it's going to wait right here for one of those slots to fill up. So this is bounding our concurrency. So now that sixth go routine is sitting here waiting, or that sixth iteration of the loop is sitting here waiting, about to waiting for a slot to free up. And one of the slots will free up, right? One of the go routines will exit. And when it does exit, it's going to pull something off the semaphore channel and release one of those concurrency slots. It's also going to tell the wait group, hey, I'm done with a unit of work. So that's going to happen. And when that happens, this will free up that waiting go routine to continue moving forward. So what happens here is we're basically doing concurrently work, but in units of 5 at a time, right? At most 5 at a time. Let's see what this does. And really, the code doesn't change much here, right? It's kind of the combination of what you saw before with the wait group and the channel. The only difference is we're using a buffer channel here that can hold at most 5 things before blocking and waiting. And that's kind of the code here. So let's look at this. So if we run this with the semaphore way, you'll notice that same idea. It's still out of order execution, but it's kind of like out of order execution in units of 5, right? Like it's like this group of 5 is out of order, and then this group of 5 is kind of out of order, and then this group of 5 is kind of out of order, and this group of 5. And it's like, if I were to put like a print line somewhere in here, you probably can see that a little bit better. But the idea is you're still getting that non-determinism, but now we're running it in at most 5 go routines at a time, and we're using those 5 go routines to process all 20 of these folders, right? Or all 20 of these files. And you'll notice that this is significantly faster than the serial way, right? Serial was like 120 milliseconds. It is slower than just tossing all go routines out into the wind, but now we're safer, right? If I had 20,000 files, I'm only going to do them at most 5 at a time. So I'm protecting myself. I'm being more defensive in my programming here, and I'm not letting the fact that I'm doing concurrency take down my application. Cool. I want to show you one more thing in the code, kind of. And the idea here is that we're using the semaphore, right? We have this going on here, and the semaphore here is like protecting us, right? You can tune this semaphore though, right? Like I could have said like do 20 at a time, right? If I did this, look what happens. Boom. The semaphore way is just as fast as the wait group and channel way doing everything, but it's still bounded, right? It's just bounded by all 20 files. So you can kind of tune the amount of like workers you have, or the amount of the bounded concurrency you have, and find the sweet spot for your application. Now, you might be asking yourself, like, hey, Matt, what's the difference? Like, how do I know how to tune that semaphore, or how do I know how to tune my concurrency to like get me the most benefit? And really, I'm just going to kind of talk to you about it a little bit and say like, let me go back to the code, because I think that'll make more sense if I show you the code. So think about the work we're doing here, right? We are reading files. Files are an IO operation on your computer, which means it has to go to the kernel. It has to say, hey, kernel, I want to read a file. Please give me like a buffer to read, and blah, blah. It has to like do this IO operation, right? Similar to making a network request over the internet. There's IO involved. When you have an IO bound workload like this, it's kind of okay to spawn a large number of go routines and like let the kernel deal with that, because you're really just waiting on the IO to complete. That's not killing your CPU in your program. That's not like hurting your resources in your program. You were literally waiting for the disk to read, or the HTTP request to come back, or whatever it may be. So when you have an IO bound workload, you can kind of scale up your concurrency to be a higher number than the number of like threads you have on your CPU, right? Because the bounding here is the IO. But if you were doing a lot of CPU intensive work that required use of the actual processor, well, then having such a high concurrency bound that's like greater than the number of threads in your CPU is actually going to hurt you, because you're going to spend more time context switching, and you're going to like take the cache lines out of your CPU and blah, 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 and do all this stuff. And what I'm trying to say is, you don't really know what this number is going to be, right? Like I don't know to set this to 20 or to set this to 0 or 1 or whatever. Like I don't know to set where to set this unless I know what the workload is that I'm processing. Since I know that this is a IO bound workload, I can kind of get away with setting this higher than the number of threads I have. But if this were a CPU bound workload, I couldn't do that. So to kind of get around this, Go ships some things in the runtime package. So they have like num CPU in the runtime package that'll tell you like how many logical CPUs the current process has to use. You can use something like this to like limit your concurrency. You can also do other calculations depending on your benchmarks and whatever. But the point I'm trying to make here is it doesn't really, you can't start configuring this stuff and making your concurrency better or worse until you have a better understanding of the actual workload that you're running. Cool. And that's really all I wanted to show you. If you have any questions on this stuff, I know I didn't like go into super like detail around, what exactly is a Goroutine or a channel or blah, blah, blah. And I kind of didn't really want to. I wanted to show you, I wanted to show you all of them running at the same time before I called it. I kind of wanted to just show you like the difference of this patterns, right? Like you can see this right here. Serial, 120 milliseconds-ish. Wait group in channel, like unbounded concurrency, 5-6 milliseconds. And then a semaphore, 5 milliseconds when I let it go wild and less when I constrain it a little bit further. So like you have these little knobs to turn. You shouldn't be afraid of concurrent programming. Get out there, start using Goroutines, start using channels, and ask these questions, right? I didn't want to make this a video about exactly what a channel is and this and that, because you can find that information out yourself. I just wanted to show you these sort of patterns and more of a practical example of how you can do this. So yeah, I hope you enjoyed this video, and I'll see you in the next one.